Hi class, it's time to start the lecture on Chapter 31, which is on disorders of fluid and electrolyte balance. I'm going to start with telling you the big picture. First, we're going to review why water moves, and we will review why water, or plasma I should say, moves out of a capillary bed during the filtration process and becomes interstitial fluid. And then we will discuss, again, why edema can develop during this process. Then I will switch the focus to osmolality and milliosmolality, which are terms that allow us to quantify the number of particles per kilogram of solvent in our body fluids. Of course we are concerned with the number of particles because they have pulling power on water movement across cell membranes. Our lecture is on water imbalance, which is why we're reviewing some of these older topics. Electrolyte imbalance, and electrolytes can have pulling power, again that's why we're reviewing. Body fluid expansion and contraction with or without salt changes, and then we'll finish with discussion of potassium imbalance and types of cardiac dysrhythmias that we can expect in a patient with potassium imbalance. We can easily spend an entire semester on this topic alone, so I'm just highlighting a few electrolytes with how the body maintains their balance and problems that can arise when they are in imbalance. We have two basic body fluid compartments, which we have already learned, of course. We have the intracellular fluid compartment, with the intracellular fluid being most abundant in potassium. That's one electrolyte we're going to cover today. And then, of course, there is the fluid outside the cells in the extracellular fluid compartment. The intracellular fluid is about 40% of our body weight. We are walking sacks of dilute aqueous solutions. About 60% of your body weight is from water. 40% of that, or 2/3, is found inside the cells in the form of intracellular fluid. You have roughly 100 trillion cells, so it stands to reason that most of your water would be found inside those 100 trillion cells. The rest of your water weight is found in the extracellular fluid compartment. The ECF compartment is broken down into three smaller subcompartments: interstitial fluid, plasma, and the transcellular compartment. The interstitial fluid is the fluid that immediately surrounds the cells found in the tissues. Plasma is the fluid that surrounds the formed elements of blood. The plasma doesn't include the water inside the formed elements. For example, inside the red blood cells, white blood cells, etc. Because that would be intracellular fluid, wouldn't it? So whole blood is really a mixture of two fluid compartments. Transcellular fluid is surrounded by epithelial cells. This fluid includes synovial fluid found in the synovial joints, or the fluids found in your peritoneal, pericardial, and pleural cavities, for examples. So the largest body fluid compartment, again to say it, is your intracellular compartment, followed by the interstitial fluid, then plasma, and the smallest compartment is the transcellular compartment. And the pictures here are just highlighting some of these body fluid compartments. The first question mark would be showing you intracellular fluid, the one in the red blood cell, again showing you intracellular fluid, the one surrounding the red blood cell representing plasma, and the last question mark that just appeared here is showing you fluid that would be in between cells, and that's the interstitial fluid. And the one in the lumen of the stomach would show you transcellular. Water moves for two reasons. Let's start with the bottom bullet first, hydrostatic pressure. That is the pressure that the fluid exerts on a vessel wall or container. If you have a water bottle in front of you, or some type of beverage, that beverage fluid exerts a pressure on the container wall, and the container, of course, exerts a pressure right back on the fluid inside. If you were to squeeze on a water bottle, that force causes the water to move, and you are demonstrating hydrostatic pressure at its best. It is hydrostatic pressure that causes our blood to flow through our vessels, even when our heart is at rest. We call this blood pressure, and it is the same pressure that causes plasma fluid to filter out of a capillary bed and become interstitial fluid. Hydrostatic pressure does not explain why water moves across individual cell membranes, and the reason for that is because cell membranes are flexible, almost fluid-like themselves. Osmotic force is the other reason why water moves, and explains why water moves in or out of individual cells. What is an osmotic pressure or force? Osmotic pressure develops across cell membranes when there is an unequal number of particles per unit of volume. When we think of a greater number of particles on one side of a cell membrane, of course we think those particles would automatically diffuse down their concentration gradient and reach equilibrium. However, most particles in our body are water soluble and cannot move across the hydrophobic region of the cell membrane. So if particles are unequal across the cell membrane and they are impermeable, then water will move to the side of greater particle count in an effort to dilute those particles in a larger volume. I always like to say, particles suck. So osmosis is the movement of water, the diffusion of water from an area of high free water concentration, or low particle count, to an area of low free water concentration, or high particle count. It is easier for physiologists to measure the solute concentration instead of the amount of free water, and therefore the unit osmol refers to a number of particles. It is important that you realize your body fluid compartments have different volumes and different composition. That means different types of particles are found in the different compartments. For example, sodium is most abundant in the extracellular fluid, and potassium, like I said in the previous slide, is most abundantly found in the intracellular fluid. But your body fluid compartments should have the same number of particles per unit volume. If not, then water will move. Your body fluid compartments may be different sizes and have different composition, but they all should have the same number of osmoles or solutes in a liter or kilogram of water. In fact, the magic average number is about 280 milliosmolal. Let me tell you a quick story to help with this concept. When I was pregnant with my youngest child, I had gestational diabetes. My favorite drink that I was allowed to have was Crystal Light. My oldest, then 4 years old, offered to make me a glass of Crystal Light. He went into the kitchen and poured an entire tub of Crystal Light into a single glass. Obviously, this was way too concentrated. I went into the kitchen and poured it into a pitcher and diluted it. I then poured myself a glass of Crystal Light. I'm sure you can visualize that the pitcher contains a much larger volume than the glass, but each container has the same concentration of Crystal Light. I could have drank from either the container and the solution, either from the container or the glass, and the solution would have the same sweet taste. That's what I want you to think of for your body fluid compartments. They have different sizes, different solutes, but the quantity per unit volume should be the same. Just to highlight once more, capillary hydrostatic pressure is the primary pressure that will cause fluid to move out of a capillary bed and into the interstitial space. But it is osmotic pressure that is the primary pressure that causes fluid movement across individual cell membranes. In this picture, we are going to focus on an application. You are seeing blue and purple dots in the compartment labeled GI tract, and you are seeing just blue dots in the compartment labeled plasma. Let's say the purple particles represent aspirin molecules. The question asks, how would these particles move across the compartments? Well, aspirin is soluble across the GI tract. In fact, it is soluble across the stomach mucosa. According to Fick's law for the rate of diffusion, we need a few conditions, and two of these are concentration gradient and permeability. We clearly have a gradient of aspirin, and it is permeable. So the molecules will diffuse from the lumen of the GI tract through the mucosa into the blood in neighboring blood vessels found in the submucosa. In slide 5, the purple particles are now fiber. Fiber is a polysaccharide used by plant cells to form their cell wall. We lack the digestive enzymes to break the chemical bonds to reduce this large molecule into its individual monomers. Therefore, we cannot absorb this molecule from our GI tract. These molecules are impermeant. If you look at the total number of particles in these two compartments, you can see we have a greater number of particles in the GI tract than in the plasma. We have unequal distribution of particles. We now have a situation of a chemical gradient, but the particles cannot move, and these are the conditions required for water to move from the plasma compartment through the submucosa and mucosa into the lumen of the GI tract. This fiber has an osmotic force, causing water to move into our GI tract, and this is the reason why people take laxatives or fiber supplements to help them have a bowel movement. The water rushing into the GI tract lubricates the fecal material and makes it easier for the person to have that bowel movement. Osmosis occurs when water moves from a solution with fewer particles to a solution in an adjacent compartment that has a greater concentration of impermeant particles per unit volume. Another way to say this is particles suck, meaning the side with the greatest number of impermeant particles will have more drying power and will pull the water to that side. But how do we define osmotic pressure, and how do we measure it? Osmotic pressure is measured by the amount of hydrostatic pressure that must be applied to stop water from moving. Let me explain. Envision two chambers side by side separated by a membrane with pores that will only allow water movement. Any solutes in the solution are impermeant. In one side, let's put a 3 molar sodium chloride solution. On the other side, let's put pure water. Clearly, water will move from the pure water side to the 3 molar sodium chloride side, and the volume on the 3 molar sodium chloride side would start to rise. If, however, we were to put a piston on top of that sodium chloride side, such that we could apply a downward pressure to prevent the column of the 3 molar sodium chloride solution from rising, we could then measure how much pressure we had to apply to stop water from moving from the pure water side to the sodium chloride side. Let's say this pressure we have to apply is 600 millimeters worth of pressure, millimeters of mercury. How would this number change if we use 6 molar sodium chloride instead? Well, then the amount of pressure we would have to apply would jump to about 1200 millimeters of mercury. This external pressure we are applying is, simply put, hydrostatic pressure. In other words, when the hydrostatic pressure is equal to and opposite in direction to osmotic pressure, then there will be no net gain or loss of volume. And this is how we measure osmotic pressure of solutions in a laboratory setting. Putting this back into a clinical setting, if you have a patient with unequal concentration of particles per unit volume, these particles are mostly impermeant in the human body. Water will move to the side with the highest particle count per volume. That is, the side that will gain the water volume. We will see this in 6 examples of water contraction and expansion. Let's use an example of uncontrolled diabetes mellitus. Notice in the blood vessel here I have many S molecules to represent glucose. Glucose has a molecular weight of 180 grams per mole. I cannot get into the cell, and it cannot get into the cell without a transporter. Without insulin, the cells don't insert this transporter, and therefore glucose is rendered impermeable. This means that the blood plasma now has a 304 millimolar or osmolality concentration instead of the normal 280 to 300 milliosmolality. Now, this plasma compartment has a higher particle count compared to the surrounding interstitial compartment and intracellular compartment, which are still at 200 milliosmolality. Water will diffuse out of the surrounding cells and interstitial spaces into the blood vessel in an effort to dilute the plasma compartment. This means that when and if equilibrium is reached, the surrounding tissues will have lost water, and this means the person is now very dehydrated, and still the osmolality of the blood plasma is higher than it should be. Let's review this concept and define some vocabulary terms. Many textbooks interchange tonicity and osmolality. Are they truly synonyms? No. Tonicity refers to a solution with more or less particles than the cell, and these particles are effective osmoles. That means they are impermeant. As a result, water will move across the cell membrane. The term osmolality simply refers to the number of osmotic particles per unit of solvent mass. It does not address whether these particles are impermeant or not. Let me put it another way. If you said, Kara, I'm putting your cheek cell in a hyperosmotic solution, all that tells me is that the solution my cheek cell is going into contains more particles than my cheek cell per unit of solvent mass. If you said, Kara, I'm putting your cheek cell in a hypertonic solution, now that tells me that not only is my cheek cell going into a more concentrated solution, but also that the particles in that solution cannot diffuse, and now I know the fate of my cell. It will lose water and crenate. Another way of saying this is, stating if a solution is hypertonic or hypotonic tells us more details. It tells us the solution is not the same in particle count as the particles in the cell, and the particles cannot diffuse. Therefore, water will, and the cell will change shape. Why don't we just use tonicity and delete osmolality from the books? Well, there are some solutions we use with particles that can cross the cell membrane, like urea, for example, in which case you would use only osmolality to describe the urea mixture with respect to its particle count. But over time, it would be isotonic because urea can cross the cell membranes, for example, red blood cell membranes. And this would not cause the red blood cells to change shape nor volume. This slide shows us a quick way for the clinical caregiver to calculate the osmolality of plasma. Normal osmolality has a range of 275 to 295 milliosmolality, which is why most textbooks just round up to about 300, whereas others stick to the middle and use 280 milliosmolality. This equation is from your textbook, so let's walk through it. When you get your patient's blood work back, you can take the sodium levels given in milliequivalents per liter and multiply by 2. Additionally, take the glucose levels and divide by 18, and take the blood urea nitrogen levels, or BUN, and divide by 2.8. Then you would add all three of these together to determine your patient's blood osmolality. 1 milliosmol of glucose has a molecular weight of 180 milligrams per liter. Another way of saying this is 180 grams of glucose per liter would equate to 10 osmol solution of glucose. And 1 milliosmol of urea equals 28 milligrams per liter. I'm sorry I misspoke in that previous example. It should be 180 grams of glucose per liter would equate to 1 osmol solution of glucose. My mistake. So why are we doing this whole division part of glucose and urea as 18 and 2.8 instead of 180 and 28? Because that's confusing, right? I just got my math mixed up. Notice that the values for the patient's glucose and bun are given in milligrams per deciliter. A deciliter is a tenth of a liter, and therefore we would need to divide the milligrams by 10. That is why we use 18 instead of 180 and 2.8 instead of 28. These three molecules represent the particles in the plasma with the greatest osmotic effect. Notice I didn't say only, as albumin, of course, contributes. And others. Sodium, glucose, and bun are the three we focus on for calculating blood osmolality. But still, we recognize no nurse is walking around with a calculator to divide glucose values by 18 and bun by 2.8 to add to twice the values of sodium. Clinically, the shortcut is just to multiply the sodium values by 2, as sodium by far is the most abundant solute in plasma. As such, if we had to reduce all the components in the plasma to just one that has the most pulling effect on water, it would be sodium. But why do we multiply by 2? Because sodium came from an ionic compound, sodium chloride. When this compound is placed in water, it not only dissolves, but it dissociates, breaks apart into two ions, sodium cation and the chloride anion. 2 particles for every 1 sodium chloride compound. That is why we multiply the sodium values by 2. You might be wondering why we don't do something similar for glucose or the bun or urea. Let's just address glucose. Glucose is C6H12O6. Glucose dissolves in water, but does it dissociate into individual atoms? Does it break down to 6 carbon atoms, 12 hydrogen, and 6 oxygen atoms to give us 24 particles? No, it does not. Glucose and urea are molecules that have covalent bonds. Therefore, they count as one intact molecule, or one particle. Something else to discuss. Why do we use milliequivalents per liter when we talk about sodium? Why can't we use milligrams per deciliter like we do for glucose and urea? Why 2 different nomenclatures? I can tell you why with this analogy. Let's say you are going to throw a party and you say to yourself, I will invite 1,000 pounds of males and 1,000 pounds of females. In your head, this sounds like each gender will be equal in weight. But if we recognize that most men weigh more than women, you might have a party with more women than men. Their total numbers will not be equal. The same concept can apply to ionic compounds. With ionic compounds, we recognize that they have different molecular weights. But it is crucial that charges are equal when we are speaking of electrolytes in the plasma. We need equal amounts of cations and anions. Therefore, the term milliequivalents tells us how many equivalent plus charges there are, in the case of sodium, for example, and we could do the same for chloride, milliequivalents of negative charges. Sodium could represent the women in my analogy, and chloride could represent the men. Men and women have different weights, as do sodium and chloride, but at a party we'd like to have equal men and women, just as we want to have an equal plus charge for every negative charge in the plasma. Again, for electrolyte values, they will be given in milliequivalents so that the clinician can compare charges and not deal with atomic mass. I'd like to now focus on this pulling power I keep speaking of. How many millimeters of mercury worth of pulling power does a single osmol have? 19,300 millimeters of mercury. That would mean that 1 milliosmol would have 19.3 millimeters of mercury worth of pulling power. If we stop and think that 1 mole of sodium chloride would generate 2 effective osmoles compared to albumin, a very large molecule that does not dissociate, we can quickly realize that it is the number of particles, not the size of the particle, that will generate the most pulling power on water. Let's apply these concepts of pulling or pushing water with respect to exchange across the capillary bed. Of course, we've learned in physiology about the net filtration equation, and we have seen this slide before in our class, but it warrants review. This equation addresses the permeability of the capillary and the Starling forces. We recall that the Starling forces that are the strongest are the capillary hydrostatic pressure and the colloid osmotic pressure in the capillary. These 2 forces also work on the movement of water in different directions. The capillary hydrostatic pressure will favor water leaving the capillary into the interstitial spaces, and the colloid osmotic pressure of the capillary will favor the pulling of interstitial water into the capillary. We also know that the capillary hydrostatic pressure drops across the length of the capillary bed. If and when capillary hydrostatic pressure is larger than colloid osmotic pressure, as it is when near the arterial side of the capillary, water from the plasma will move from the capillary to the interstitial space. When capillary hydrostatic pressure drops below colloid osmotic pressure of the capillary bed, as what happens when the blood flows towards the venous end of the capillary bed, then the interstitial fluid is pulled back into the capillary. These forces dictate the exchange of plasma and interstitial fluids and the exchange of gases, nutrients, and waste products. These forces are the reason why capillaries are called exchange vessels. Across capillary beds, it is the hydrostatic pressure and colloid, think albumin, osmotic pressure in the capillary bed that causes shifts of water across the capillary lining. Conversely, it is the osmotic effects of sodium, glucose, and bun that will dictate the shifting of water into or out of individual cells in the body. You might be wondering why albumin has the greatest control for pulling power in a capillary bed when we just discussed in the previous slide how much pulling power sodium, glucose, and bun have in the first slide. Answer: sodium, glucose, and bun can go with the plasma water to the interstitial space, and therefore they are relatively equal in quantity in the plasma and in the interstitial fluid across the capillary membrane. Albumin does not cross the capillary lining due to its large size, and therefore it remains in the capillary bed as the main pulling force to draw fluid back. Additionally, albumin is the most abundant protein found in the plasma. It is appropriate now to review some causes of edema, specifically the pitting type. This means if you were to squeeze on the edematous patient, as shown in this bottom picture, your fingers would sink into the person's flesh, and you would leave behind a pit where your fingers just were. There are 4 main causes of pitting edema. 1. Changes that lead to increased capillary hydrostatic pressure. 2. Changes that lead to decreased colloid osmotic pressure. 3. Changes to the Kf, or the capillary permeability factor. And 4. Obstruction to lymphatic flow. I don't want to bore you by reading every example for each category, so let's just pick a few examples. If a person has increased capillary pressure because of increased salt and water retention, like listed here for premenstrual sodium retention, then this will lead to increased capillary hydrostatic pressure, and it will favor outward flow of filtrate from the capillary into the interstitial space. This is the reason why women complain of being bloated when they are premenstrual. Loss of plasma proteins through denuded skin, such as seen in severe burns, will lead to a decreased pulling effect of the capillary colloid osmotic pressure. Of course, we have already covered the starving child in kwashiorkor and the person who is malnourished, such as the alcoholic or the elderly in a home. Allergic reactions and the inflammatory response lead to histamine release, and histamine will both change the permeability of the capillary bed as well as lead to increased arterial diameter, which will lead to a greater capillary hydrostatic pressure. So we could put histamine in the top category here as well. Lastly, you are seeing a child with a filarial infection leading to elephantiasis. The worms, of course, are blocking the lymphatic vessels. We could also see edema in the upper member in a woman who has had a mastectomy with surgical removal of the lymph nodes.